All right. Our first problem involves the common ion effect. We're given information about an acid and potassium nitrate. Yes, it is. One thing I want to point out, the acid is going to be the major part of this particular reaction. Do you agree? Give me reasons why you think that's correct.
Because you have
It's a K.
We are given a Ka. Good. What else? Another big clue. Tells us to calculate something. pH. pH and Ka mean acid-base reaction. You agree? Okay. So the acid in this particular case is labeled acid. The common ion is not so obvious, but is, of course, the potassium nitrate. And what we're going to look for is an ion that has something to do with that acid. So let's start with the reaction. Always start with the reaction. What are we going to add to the acid?
water.
Water. The acid is, of course, going to donate its proton to water and form the conjugate base and the hydronium ion. One thing I hope you remember from way back when we talked about salts is they do tend to dissolve into the two parts. Remember that from doing our different reactions with precipitation and things of that nature. Okay. One of these is the conjugate base's common ion. So you have to recognize that that is a common ion because the next thing to do is set up our ice table, our Ka expression, solve for X, all of that lovely stuff. We're asked what the pH of the solution is going to be. And remember, just like we did before, the first thing we're going to do is we're going to ignore X to double check if it's okay to ignore X. Yes?
Since just asking for pH points, would it be okay to just use a Hendrix equation thing?
No. Henderson-Hasselbalch only applies to buffers. So when you see the term buffer, that's when you can use the Henderson-Hasselbalch. Good question. Here we are. What do we do next? Drop them down. Remember that we are going to make the assumption at first that we can ignore X. We're going to prove that to ourselves before we make any further assumptions. Our Ka expression then should be products over reactant. You were given a Ka value, right? We've gotten this far. What do we do next?
Solve it.
Solve for X. I want to hear what you get.
1.275 times 10 to the negative 4.
It's my first answer. I need at least two people to confirm it. Keep looking. Keep mathing.
That is not what I
No.
Would you-
I got 3.8 and 5 times 10 to the negative 4.
There's another answer I got. I got 2 people who got that one. You got the second one?
Yeah.
Second one? Okay. I'm sorry, you've been outvoted.
It's fine.
You spot your error?
No.
So multiply over 4.5 times 10 to the negative 4th. Make sure you're using your parentheses. It's a big one. I don't know where my calculator is, otherwise I'd do it for you. Can we see my calculator?
Did you lend it out?
I always lend it out. But it's so important, I need it back.
You want to borrow it later?
I want to find my calculator. Oh, yeah. Oh, yeah.
I think, doesn't it have to be like negative to the negative?
So remember, it has to be it has to be 2 orders of magnitude. That's the term. Different than the smallest number. This number is 8.5 times 10 to the negative 2, right? If this number is times 10 to the negative 4, that's 2 orders of magnitude different. So can we ignore x?
Yeah.
Yes, we can. But you have to prove it to yourself. Again, x has to be, should be, 10 to the negative 2 different. It must be. Yes.
So when we're like, if it's at least two magnitudes like less,
Correct.
so when I like plugged it back into like to check it, it's like 0.082. Is that fine as long as
Close enough.
Perfect.
Why is that 10 to the negative 2? Like, I don't get it in terms of the decimal
Oh,
placement and stuff.
like
Like 10 to the negative 2 instead of 10 to the negative
1,
1.
2.
Okay.
That make sense?
Okay.
Where do we check it with?
Check it.
Like, how do you like plug it?
You're just so
Yeah.
you're just comparing the two, right?
All right.
You could plug it back in. You could do 0.085 minus this number and see what the difference is if you really want to check it. But if it's 2 orders of magnitude, you're good.
No, I'm kidding.
Okay, so that means, can we assume that this is the concentration at equilibrium of this, and this is the concentration at equilibrium of this?
Yes, ma'am.
We can also assume that X is the concentration of H3O plus, right? What do we do with that to get pH?
You take the negative.
So we're going to do pH equals the negative log of the concentration. I guess is like 3.9. I like to guess, but I really can't see log.
It's 3.42.
That was close. That was really close, actually. Oh, ballpark. I can't do log math in my head. Okay. Are we done?
I'd be scared if you did.
That was the goal. Okay. So your question of can we just pretend like that's the concentration at equilibrium doesn't apply to this problem, right? You have to solve for X to get your H plus concentration for this problem. Do you see? Okay. So a lot of the questions you're asking are depends on the situation. You have to look at the situation before you make a decision about what can you ignore and what can't you. In this case, did it matter that we ignored X? Not really. If we go back and we solve it and we don't ignore X, we're going to get a number like 3.46. It'll go up a little, but it won't be a lot. All right. Let's do another one. Set it up. Try to get the equation first. If you're given a Ka, you can assume the Ka that you're given is going to involve itself in the actual reaction. That should give you some hint. We are supposed to be finding the formate ion concentration, and we're given formic acid. So there's my formic acid. What am I going to do? Going to remove a proton. up my ice table. We were given a Ka. Can we write a Ka expression? Of course. Without knowing anything else, you should be able to get here. You should feel pretty comfortable about getting here at this point. Done a lot of acid-base equations, done a lot of K equations. Should be able to at least set this part up. From here, it's interpret information you're given. So, we're told we have a 0.050 molar formic acid solution. Seems like that's where that number goes. Next thing we're told is that we have a 0.10 molar HNO3 addition. All right, so if this is an acid, does it look like an acid?
Yeah.
It's going to dissociate, right? So where's the common ion concentration going? That's my H3O plus concentration. So my 0.1 molar goes over here. Now what?
Ignore water.
Let's do some x's. This one's a 0, right? So which side are we adding x, left or right? Do we always add x to the right side?
No.
No, we do not. Do not say yes to that question.
Find out.
Because sometimes we go backwards. We've done that before.
Mm-hmm.
Not often, but sometimes we go backwards. How do we know to add x to the right side, though? Because of the 0. Can't subtract from a 0. Molarities don't work that way. All right, dropping them down. Formate ion is this guy. Yes, ma'am.
I'm still confused on how you put the HNO3 and make it the H.
So anytime we're dealing with our common ion effect problems, we need to figure out what ion is present. And in this particular case, when we dissociate, so what you should do whenever you're given those is dissociate them into their two parts. One of the two things should have something in common over here.
Oh, okay.
That's the one that has the thing in common. You remember that H plus is the same as H3O plus? We use them interchangeably?
Okay.
Okay. All right. Here we are. Our goal is formate ion concentration at equilibrium, correct? So we have to solve for x. Can we ignore x to start?
Or about the frame.
The subtraction or addition of x is one we can ignore. We're going to prove to ourselves that we can do this by solving for x without the change. So now we're going to plug it in. This is my equilibrium, equilibrium, equilibrium. I get what do we get for x? 10 cents to the negative. I got two people.
Yeah.
You got that? You got that? You got that? If you didn't do it in your calculator, don't agree. All right, is that number at least 2 orders of magnitude different than the ones you had at equilibrium?
Yeah.
Absolutely. That one's like 3 orders of magnitude different than most of them. Okay? All right, so we're going to use that x value for our HCOO minus concentration, right? So that's the answer to our problem. All right, the problem you're going to do on your own is number 1. You're not going to do it now. We're going to work on the next set of things. First, buffers. We're saving acid-base titrations for tomorrow.
Oof.
Okay. Can I erase?
Sure.
We good? See, the hard part of common ion effect problems is identifying the common ion. The rest of it you've done over and over and over again. You've done ice tables, you've done pH calculations, all that lovely stuff. All right. Put that puppy up there to remind us. Next thing we're going to look at is the actual question. Calculate the pH of a buffer composed of 1.12 molar benzoic acid. We're given pKa. That's nice, we don't have to do that calculation. And 0.20 molar benzoate. Now we are given both of the chemical formulas, so hopefully you see that this is the acid because of the H at the end. And hopefully you see that this is its conjugate base if you just pretend you don't see the sodium, right? Sodium benzoate is technically a salt when we put it into solution. Oh gosh, big one, isn't it? C6H5. Okay? Sodium benzoate, when we dissolve it into our, excuse me, two parts. This guy, hopefully you recognize. This is the reaction we're dealing with, correct? We take our benzoic acid, add it to water, form the benzoate ion, and that H3O+. Okay, so this sodium benzoate that we were given must then be the conjugate base. Do we see that? Hopefully. All right, so figure out what the pH is. What do we get our pH to be? Is that what you got? Sure. Yeah. What you got? Got a couple of people who agree. Is that what you got, Noel? Okay. So there's our pH of the buffer. All right, next up, let's do the exact same reaction. So it's benzoate concentration is our question instead. Oh boy. Okay. Well, our pKa is still this, right? And we're told a 0.2 molar solution of acid. Okay. So we're going to use the Henderson-Hasselbalch slightly differently here. Let's plug in what we know. Oh boy. Who remembers the property of logs?
All that stuff right there, that's for number 2, right? Like
Yep,
on the
this is
slide.
number 2.
Okay. Just
Yep,
making sure.
it's the same base, same acid.
Okay, I thought so, but I just want to make sure I read it.
Yeah, you still have it labeled number 1 there. That kind of threw me off.
I meant that was like the homework problem that
Yeah,
you're
of
gonna.
course,
So you're gonna
yeah.
do numbers 1 and 2 on your own in the next section, but I don't want you to go beyond that. You're okay.
1 for 17.2 for homework.
You're finishing your outline for homework, technically.
Probably should do that.
I know you guys probably learned the property of logs. Does anybody remember what it is? If you have two things that are being divided, what do? You subtract them. Cool. That's okay. Let's do it together. We're going to move this over, right? We're going to get negative 0.204 equals the log of the concentration of X over 0.20. I know for a fact you cannot see how to solve X with that log. You don't divide both sides by log, guys. It's not a thing. Instead, we're going to use what we call the property of logs. I could have sworn this was a pre-cal thing, but maybe it's a pre-cal thing you haven't gotten to.
I'm not in.
Emma, is this the thing you learned at the end of pre-cal?
Doesn't you use E?
I didn't learn any of that.
Isn't it like log of x minus log of
Yes. So log of A over B, we can set that equal to, so we can basically replace it with
Oh, no, we did learn this.
that.
No,
I know you learned it. It's just been a while. It's okay. So here's how we're going to separate the fraction. We're going to take what we know and we're going to subtract them instead. Okay? So this is going to become the log of x minus the log of 0.2. Okay? Hopefully you're seeing that we're getting closer to an answer. We can solve one thing. We can't solve a fraction. Okay? So what are we going to do next? We're going to add the log of 0.2 because that's just a number, right? Put that in your calculator. Log base 10 of 0.2 comes out to be what? I, again, don't have a calculator. Someone else has to do it.
Negative 0.699.
699?
Yep.
So aren't we subtracting it then? So it's negative 0.204 minus 0.699 is what?
No, this is negative 0.8.
Yeah, because the signs are weird.
So then you'd be adding them together.
So you get plus the log of 0.20, and the log of this is a negative number.
negative 0.93, negative 0.903.
What?
This is what it becomes, correct?
Yeah,
So what is that number?
negative 0.903.
And then you just take a log of both sides to solve it.
You do 10 to the, remember, to get rid of the logs? I'm going to continue my math over there if no one has an objection. So here's what I've got. 903, is that what you said? How do I get rid of the log on the right side? How have we solved logs in the past?
10 to the negative.
10 to the. So 10 to the log and 10 to the negative 0.903. So we're going to get 10 to the negative 0.903. We're not going to change the sign. What does that come out to be in your calculator?
0.125.
There's our answer. Hopefully that kind of makes sense to you because in the previous problem, we had a 0.12 molar solution and our pH was slightly different. Okay. Different way of using the Henderson-Hasselbalch. The big thing here is remember the property of logs. It's one I would give you in case you needed it. All right, move on to the homework. The end of this document, the second page, I guess, you can do numbers 1 and number 2. Those are both about the common ion effect and the buffers. Yes, ma'am? You're looking at the appendix for the actual KAs, right? Yeah. It's like the end of the book. That's what an appendix is. Yes? Grab a book, look at the appendix. You haven't seen the appendix since the end of last semester. We used the appendix a lot last semester.
Last semester
We were
was a
using
long time ago.
notations.
You wanna know why?
That's why everyone's freaking out. The actual
Stick it in the microwave and your homework will be on.
I'll stick your whole book in the microwave. All your homework will be gone.
Really?
Yeah.
All right, get to it, please.
Create friction, which
We got plenty of time to finish it.